We are starting chapter 5, topic 5, in our new books. Yay. And the topic, can you turn back a page or two and tell me what the topic title is? The topic title at the very beginning of the topic says, Analyze and solve systems of linear equations. Systems of linear equations, guys. Do you know what a linear equation is?
Yes.
Yes, it's an equation that does what? Makes a straight line on the graph, right? So that's a linear equation. So a system of linear equations means we're going to do two lines on the graph at the same time.
Whoa.
Oh my goodness, how challenging is that going to be? But you know, two lines at the same time ought to be twice as hard as one line at a time, right? But we're going to be looking at equations, we're going to be using x and y variables, we're going to be graphing stuff, we're going to be looking at the solutions to those equations, all right? So, today we start with lesson 1, and I'm using this program more because for the recording I need to do quite a bit of writing today, so it shows up better on the recording when I write on this program. So I've got most everything copied over into these slides, and then the little video part will be in the other. So, but it should be pretty well all the information we need here. So we're going to estimate solutions by inspection. What does it mean when you inspect something? You just look at it closely, right? So we're just going to look at the equations, maybe do a little manipulation of the equations so that we can look at them and tell what they're going to do. All right? So really not a lot of graphing today, but looking at the equations to kind of think about what the graphs would do. Does that make sense? And then the essential question of today, we're going to be looking at those equations specifically to see the slopes and the y-intercepts. Is that hard to do in an equation? Not if the equation's in the right form. Okay, if it's in slope-intercept form, the slope and the y-intercept are right there. The numbers are there for us to look at. And so we've got to get them into the slope-intercept form, though, for us to be able to use those tools. All right, so warm-up today says, and I changed my page a little bit, doesn't look quite like yours, but it's got the same information on it. Draw 3 pairs of lines, each showing a different way that 2 lines can intersect or not intersect. How are the lines in each pair related? So, first way, I think, is probably super simple. If you have 2 lines on a graph, what does it look like if they intersect?
Cut a plus sign.
They cross each other, right? So, whoops, that's weird. Let's try that again with maybe some color added into it. There we go. Okay, so if you have 2 lines that intersect, then, well, doggone it, right there it is, right? That's the intersection. That's going to be a very special point for us as we move forward. That's going to be called one solution. Okay, those 2 lines have one solution, or that system of equations has one solution. And we want to be able to find that solution. If you have a graph, it's super easy to find it. There it is. I can see it. That's where they meet. Okay, now, what other type of scenario could I have? Do lines have to intersect?
No.
Okay.
It could be
Ooh, what's that word if they don't intersect?
parallel.
Parallel. So if I have these 2 lines and they never intersect, they're parallel. So how many solutions do you think they'd have? 0 solutions, right? So if 2 lines never intersect one another, then they have 0 solutions, all right? And they are parallel. What do you think is going to be true about the slopes of those 2 parallel lines? The slopes are 0 because they're horizontal, but what about any 2 parallel lines? What if 2 lines are parallel, what would you say about their slopes? They're the same, yeah. Parallel lines will have the same slopes. Okay, so we're going to be looking for that when we look at our equations. And the third one, so this has one solution, this has no solutions. The third possibility is a little bit harder to maybe just to kind of come up with. But what do you think it might be if they have one solution, no solutions, or any thoughts? What if I did this? I have this line and I wrote an equation for it. And then I came up with another equation, and when I graphed that equation, it did this. It went right on top of that line, and I didn't do a great job of drawing that, but how many solutions would that be if they're right on top of each other? Infinite solutions, okay? So we can have two equations that look different. This is where it's gonna get a little bit tricky for you guys. This is where it gets a little bit tricky. We can have two equations that look different, but end up being the same line. Okay, and we'll try to learn how to recognize those maybe ahead of time, even before we have to do a whole bunch of work. Because if you know what to look for, they're not hard to see. You just have to know what to look for. Okay, and we haven't really done that yet. All right, so is it possible for any of the pairs lines the lines drawn to have exactly two solutions, 2 points in common? Can you draw two straight lines and they cross each other in only two spots?
Yeah.
Not if they're straight. If they're linear equations, if they make straight lines, they can't have two solutions. Okay? Because in order for that to happen, you'd have to bend one of the lines, right? You'd have to make it go like this, or it would have to have a curve in it so that it would have two solutions, right? Can't do that. So, if it's a linear equation, then you only get one solution, or no solutions, or infinite solutions. It has to be one of those three. Does that make sense? Okay. Here we go. Oh, look. A video. There it is.
How can you determine the number of solutions of a system of linear equations? Think about this question during the lesson. Deanna drew the 3 pairs of lines below. Each pair represents a system of linear equations. A system of linear equations is formed by 2 or more linear equations that use the same variables. How can you use the graphs to determine the number of solutions of each system?
Well, using the graphs is pretty easy. Can you see the number of solutions? Can you see that this has one solution? Yeah, they cross in one spot. Can you see that these are no solution? Yeah, you see that the lines are parallel. You can count the slopes to be sure, but you can make sure that those are never gonna touch, right? And then if this one is labeled with 2 different equations and but there's only one line, that makes it pretty obvious that those 2 equations have just infinite solutions, right? So as long as you have a graph, things are really, really simple. Does that make sense? As long as the lines are on the graph, they're easy to see. But it's when you take the graph away and you have only the equations that we have to be a little bit sharper about it, okay? Here we go. Next.
A solution of a system of linear equations is any ordered pair that makes all equations in the system true. The equations of the first linear system have different slopes. The lines on this graph intersect at only one point. The system has one solution, the ordered pair, 1, 5, or x equals 1 and y equals 5. The equations of the second linear system have the same slopes and different y-intercepts. The lines do not intersect and never will. They are parallel lines. So, this system has no solution. The equations of the third linear system have the same slopes and the same y-intercepts. The lines intersect at every point. They're equivalent equations, so they are the same line. This system has infinitely many solutions. Comparing the equations in the linear system can show you whether the system has 0, 1, or infinitely many solutions. When equations in the linear system have different slopes, the system has one solution. When a linear system describes parallel lines, the system has no solution. When a linear system describes the same line, the system has infinitely many solutions. How do the points of intersection of the graphed lines relate to the solutions of the systems of linear equations?
All right, we're not going to do much of this activity because it takes us to a Desmos screen that you guys can't really do unless you get your Chromebooks out, and I don't want to mess with it right now. So we are going to do some different things with Desmos than we've done in the past. Typically, I assign Desmos and it's like a preset activity, but Desmos really is a powerful graphing calculator, and you can type in an equation and it graphs it for you, and it does some really cool stuff. So we're going to use that as we move forward on some days, just to kind of play around with the equations and see what they look like, okay? Because it can really help us understand things. But we're not going to worry about it right now.
The coordinates of the point or points of intersection x, y are the solutions to the system of linear equations. The first graph has one solution, the second graph has no solutions, and the third graph has an infinite number of solutions.
Okay, that last little summary is kind of the big idea of this lesson, and we're going to see that kind of play out on the next few screens. So how many solutions does this system of equations have? The thing that they do that's nice to us here is they put both of these equations into slope-intercept form for us, and that makes life easy, because if the equation's in slope-intercept form, it shows me the slope and the y-intercept. I think I have this on my other screen. I do, so I can write on the screen. All right, so how many solutions does this system have? Well, because they're in slope-intercept form, I can see that they have, this one has a slope of 1, and this one has a slope of 2. Okay, so since the slopes are different, that means the lines go at different trajectories, so they're going to meet somewhere, right? So they're going to have one solution. And the reason they have one solution is because they have different slopes. So the lines intersect at how many points? 1 point. Okay. So different slopes mean one solution. Here they give us a new scenario. The equations of a system have the same slope. If they have the same slope, what's going to happen? They could have infinite solutions if they have the same y-intercept, right? Because that would mean same slope and they're on the same path. What if they have different y-intercepts?
No solution.
No solution because they're parallel, right? Does that make sense? So we're looking for one of 3 scenarios. Different slope, one solution. Same slope, same y-intercept, infinite solutions. Same slope, different y-intercept, no solution. All right, so we're going to be looking for that as we move forward with these problems. Harrison and Pia each buy X comic books. Harrison also buys an action figure for $15, while Pia buys a different action figure for $12. Could they each spend the same amount of money, Y, and buy the same number of comic books? Well, let's talk about it. And I want to talk about a couple of different ways to look at this problem. One way that the book lays out for you, and another way that may be helpful to some of you, but the book doesn't really get into. So, let's first do the thing the book doesn't do. All right, because you can look at what the book's going to do for you. And it's fine what the book does. I like it. We need to be able to do that. But another way to think about this might be to make a table of data. So if we make a table of data, and this is going to be Pia's, this is going to be the information for Pia. So if Pia buys X number of comic books, she'll spend Y amount of money. Okay, that's the way we're used to looking at things. Y is the money. So if she buys 0 comic books, how much did she spend on the action figure? $12. So she buys 0 comic books, so that's 0 times 5, and then she would add the $12 to the action figure. And then she buys 1 comic book. How much does a comic book cost? $5. So $5 for the comic book plus $12. So how much did she spend? 17. Okay, and if she buys 2 comic books, that's 2 times 5 is 10, plus the $12 is 22. Okay, and if she buys 3, see where this is going? Do you see a pattern?
Yes.
Every time it's adding what? $5. So this would be 27, and then if she buys 4 comic books, that would be 32. Okay, so we can see what Pia's information is doing here. Okay, and then we could use this table to do what the book does, and the book writes an equation for it, right? This is going up by 5 every time. That would be your slope. And then our y-intercept is here where x is 0. So y equals 5x plus 12. Okay, well, what about old Harrison? Okay, har. So he's going to do the same thing. He's going to spend x, or buy x comic books for y dollars. 0 comic books cost him how much? $15, because he bought a bigger toy. 1 comic book would be 20. 25, 3 comic books, 30, and 4 comic. Okay, so we can see what they're doing. So for Harrison, what's the slope?
15.
It's 5, and then the y-intercept is 15. So 5x plus 15. Okay, and I know that's down here lower. Somebody would probably have trouble seeing it, but get over it. All right, y equals 5x plus 15. So the question is, will they ever buy the same number of comic books and spend the same amount of money? No. Can you see what's doing here? Hers is going up 12, 17, 22. Hers always ends in a 2 or a 7. His always ends in a 5 or a 0. Those are never going to line up, right? And so the slope is the same for both of them, 5, but the y-intercept is different for both of them. So what does that mean? They're parallel, no solution, right? So that's what we're looking for. We're looking for the equations to tell us what's going on. Now, sometimes if you're having trouble writing an equation, make a table. The table can help you write the equation, or it may just help you see the solution to the system as well, right? That make sense? So you can do it. There are different ways of solving these out. We need to be able to write equations, but if you're having trouble, make a table. All right. Next, we've got Corey and Winnie. And they each bought X pounds of cheddar cheese and Y pounds of tomatoes. Corey spent $12 at the supermarket. Winnie spent $24 at the farmer's market. Could they have bought the same amount by weight of cheddar cheese and tomatoes? Doesn't mean they necessarily spent the same amount on that purchase, but could they get the same combination with the way things are structured? Okay, and so let's see what Corey is doing. Corey is shopping at the supermarket, and so I think, does your book write out the equations for you? Corey spends $2 for tomatoes plus $6 for cheddar cheese, and that equals a total of $12, right? What's wrong with this equation?
There's 2 of the.
Okay, so that's not a great question. I didn't ask a great question. There's nothing wrong with the equation. What's different about this equation? The x and y are on the same side of the equation, right? It's not in slope-intercept form. That's not helpful to us, because the slope and the y-intercept is what we need to look at to know what the line is going to do, right? Okay, now can we take an equation that's not in slope-intercept form and put it in slope-intercept form?
Yeah.
In order for it to be in slope-intercept form, I need the y to be by itself. Y equals mx plus b, right? Can I get this y by itself?
Yeah.
Did I do this different than the book has it set up? What did I do different?
It's usually 6x and 2y.
I did it back, I set the variables backwards, and the way I did it's gonna cause us some problems. So I'm gonna make mine match what the book has. I apologize for that, I got ahead of myself. So I'm gonna fix this just so it matches what the book says for Corey. So the book says 6x 2y, right?
Yep.
6x plus 2y. And that's okay, I just had it backwards. So sometimes that happens, we're all right. Now, I do wanna get the y by itself, right? Okay, so to get the y by itself, what do I need to do with this 6x? I can subtract it. Subtract 6x from both sides. So that would be 2y equals, now I want my x term to be first before my constant term, right? Is it okay if I write negative 6x? And then this is a positive 12, so I'd write plus 12. Is that okay? That works. There's nothing wrong with that. It may be a little different than we're used to, but there's nothing wrong with it. Okay? Now, what do I do to get y by itself here? Divide by 2. And when I divide by 2, I have to divide everything by 2. So this gets divided by 2, that's y. So those 2's cancel out. Now negative 6 divided by 2 is negative 3x. And then 12 divided by 2 is plus 6. Okay, so now I can see what his equation would look like if I graph it. His y-intercept's going to be at 6, and his slope is going to be negative 3. Okay, that's what Corey's equation would be. Now we need to do the same thing with old Winnie Bell. Okay, so Winnie, her equation, I gotta make sure I set it up the same way I did his. So tomatoes is y and cheese is x. So Winnie spent $24 at the farmer's market, and that would be 12x plus 4y equals 24. Okay, you with me? Did I set that one up right?
Yes.
Okay. So now I need to do the same steps with different numbers. I need to get y by itself. So what's my first step? Subtract 12x. So 4y equals negative 12x plus 24.
Divide.
Now my next step is to divide by 4 on both sides. So y equals negative 12 divided by 4, negative 3x, and then 24 divided by 4,
6.
plus 6. So what do you notice about those two equations? They're the same equation. So can Corey and Winnie buy the same number of tomatoes and cheddar cheese? Yes, they can get the same amounts using the way the numbers are set up. So, awesome. Now we know they can buy the same amount of cheese and tomatoes. All right, they'll have equally yummy pizzas.
Would that be a one solution?
If they're the same equation, infinite solutions, they have the same slope and the same y-intercept. So both numbers are the same equation, same solution, infinite solutions. Okay. All right. Now, as we get better at this, then there's some things we can do ahead of time. This is a lot of work, right? I mean, there's a lot of steps here, and it's okay. We need to be able to do all these steps. But is there anything I can do up here to tell where this is going? Emery.
Well, 6x and 12x, well, it's like half of each other and then 2y.
Exactly. Okay. So 6x times 2 would be 12x. 2y times 2 would be 4y. And 12 times 2 would be 24. Does that make sense?
Yep.
Okay. As long as that's all the same, as long as it's 6x times 2 is 12x, and then I don't want to do like 4x or 4y and 4y here where it's 4y times 1, right? As long as this is times 2 times 2 times 2 and it gets me the other equation, then I can see ahead of time that they're going to have the same slope and same y-intercept. They're the same equation. Okay? It's going to be big for us moving on. Later on in another lesson or two, we're going to do a lot of that right there, okay? But if we can see that early, we're in good shape. Okay. Next slide, how many solutions does each system of equations have? Well, this first one, they did us a favor here, they put them both in slope intercept. So what about A?
The parallel.
They are parallel lines, so how many solutions?
None.
No solution, okay, and when it says explain, the explanation I would give is same slope. Same slope, different y-intercept. Okay, does that make sense? Same slope, different y-intercept, positive, negative. What do we have to do for B? We need to solve the second one for y, and we'll just call that putting it into slope-intercept form or solving it for y. We want to get y by itself. So what's my first step to get y by itself here? Add 15x, right?
I mean, not.
Yep, add 15x. So that would be 5y, not equals, minus 20 equals 15x. And then what? Add 20, we wanna get 20 to the other side. So 5y equals 15x plus 20. What would my last step be? Divide by 5. Y equals 15 divided by 5 is 3x. 20 divided by 5 is plus 4. So how many solutions? Infinite solutions because they're the same equation, right? Same slope, same y-intercept. Alright. Guys, here's the little summary. This is the big idea. If you see different slopes, it has to be one solution. That it has to be. Okay? If you see same slope, different y-intercepts, it has to be no solution. There's no other way around it. If it has the same slope, same y-intercept, it doesn't matter if they did something weird and wrote it in a different direction or different form here. As long as it has the same slope, same y-intercept, then it is the same equation, so it would have infinite solutions.
Can you keep that up there?
Sure, and it's in your book, it's on page, what, 370? It's at the top of page 270, my bad. It's at the top of page 270. Okay, so your assignment, 271, 272,
I got it.
those pages, alright?
One solution.